this video we're going to go over dimensionless groups, and we're going to solve an example using some dimensionless groups here. So we're going to be using Reynolds, Prandtl and Nussle number, and we have the equations here with the associated thermodynamic properties, which we can get from steam tables, which look like this. Basically a bunch of numbers, and this is for steam, of course, and you have the temperatures in Celsius and Kelvin. So we'll be using that later. So just some basics about the three dimensionless numbers we're going to be using, a bit about definitions of each of them, their range, as some of them may not be used outside a range, and we have some equations or correlations for forced convection that uses fully developed turbulent flow. Turbulent flow is where the Reynolds number is above 4,000. In another textbook it might be 10,000. The definition could change depending on the source. So we have three different examples of equations here. Don't need to memorise them or anything, but these are just examples of the ranges which they're applicable. So if we do an example, a shell and tube heat exchanger contains tubes with an inner diameter of 1.75 centimetres and an outer diameter of 2.65 centimetres. The thermal conductivity of the pipe is 120 watts per metre per Kelvin. Water at a bulk mean temperature of 95 degrees flows through each tube at 2,700 kilograms per hour. It asks us to calculate the heat transfer coefficient for the tube side using the Colburn equation, and we're given the Colburn equation here. So first things first, to start off, we have to find out the Reynolds number and the Prandtl number in order to calculate the Nussle number. So we need Reynolds and Prandtl. So the equation for the Nussle number is, so we have the heat transfer coefficient, the unit length and the thermal conductivity, and we're asked to calculate the heat transfer coefficient, so this value. So first we need to work out Reynolds and Prandtl. So Reynolds can be calculated in many ways, for example using density, and velocity, diameter and viscosity, but for a circular pipe you can also use 4 multiplied by the mass flow rate which we're given, divided by pi, diameter and the viscosity. So we're going to be using this one since we're already given the mass flow rate. For the Prandtl number, that's calculated using the specific heat capacity multiplied by the viscosity divided by the thermal conductivity. So to get all these thermodynamic properties that we have here, we need to use the steam table and look at the temperature of 95 degrees. So if we write down all the values we need, so we have 4 multiplied by 2,700 divided by 3/6. This is because it's kilograms per hour. The SI unit for mass flow rate is kilograms per second, so we convert per hour to per second by dividing by 3,600. And we have pi. The diameter is 1.75, but we need it in SI units, so 0.0175 in meters, and then multiplied by the viscosity, which we don't know, so we'll look that up in the table. Then for the Prandtl number, we have specific heat capacity, which we don't know. We need viscosity, and we need thermal conductivity as well. And then if we look at the steam table, so at 95 degrees, we're looking here. If mark penciled on, 95 degrees, then we can look across and find the viscosity which we need. So viscosity is here, so 298. In SI units, I've put a little converter here, so 298 here. Then for the specific heat capacity, find it here for a liquid, 4.212, and the converter is times 10 to the 3. This is because it's in kilojoules, and we need in joules for SI units. The last one is thermal conductivity, which is here, 678, and that's times 10 to the negative 3. So hopefully you can see where I got those values from. Now we're going to plug all those values into the equations. So to calculate Reynolds, we do 4 multiplied by 2,700 over 3,600 divided by pi multiplied by 0.0175 multiplied by the viscosity, which is 298 times 10 to the negative 6. So for Reynolds number we get 183,112.1, which is very large, but we can check here the application of the Colburn equation. It is above 10,000. So now we move on to the Prandtl number to check it's between these ranges. So Prandtl is the specific heat capacity multiplied by the viscosity divided by thermal conductivity. That gives us 1.85, and we can see that's between these two values, so we can use the Colburn equation. So now if we plug everything into the Colburn equation, then we'll have 0.023 multiplied by 1831121 to the power of 0.8 multiplied by 1.85 multiplied by 0.333. That comes out to 458. And as we know from the previous page, the Nusselt is a dimensionless number, so it has no units. So now that we have that, we know this, and we want to figure out the heat transfer coefficient. So we have 458 equals h multiplied, now the characteristic length is 1.75 in this case, which is the inner diameter, but we would change that to meters. So 0.0175, and then we divide that by the thermal conductivity, which is 678 times 10 to the negative 3. We rearrange and solve for h. We have 458 multiplied by 678 10 to the negative 3 divided by 0.0175. That gives us 17744.23. And the units of heat transfer coefficient are watts per meter squared per Kelvin. And that's it.